Good morning, everyone. Thanks for joining in. So I'm Sourish. I'm gonna start the lecture on object detection, and then Andrew's gonna talk about some platform tools that are tailored for deploying object detection models on specific hardware. And Anish is gonna talk about some trackers and algorithms related to that. So, oops. Yep. So what are some of the problems that are related to object detection? On the left, you can see, you can broadly sort of divide up the categories into four. So we have generic object classification. So you've given an image, you basically say what sort of objects are present in the image. Then you have generic object detection in terms of bounding boxes. So we're specifically going to focus on this particular aspect today. Then you have semantic segmentation, where the task is to annotate every pixel with a class. And then you have object instance segmentation, where not only do you do semantic segmentation, but you also instantiate between different objects. What are some of the challenges related with object detection? So typically for an ideal detector, it must accurately localize and recognize objects and images or video frames, such that a large variety of classes can be covered. So it should have high distinctiveness. It should also be robust to interclass variations among objects. And it should also be highly efficient in terms of time and memory. So today we're basically gonna take an historical overview of object detection, how it evolved as a field. So I marked 2012 as red here because AlexNet came out this year, and it sort of sparked the second revolution in deep learning. So all these methods that came before 2012, which were related to object detection, relied on classical methods such as HOG, belief propagation, graph segmentation, etc. Due to time constraints, we won't be able to cover so much today. So we're specifically going to focus on all the methods that came after AlexNet, just because it's just so dominant in terms of performance. And specifically, we're going to take sort of an overview on the methods shown in blue, and how sort of object detection evolved as a field over time from 2012 till 2020. So let's start by AlexNet. So the task for AlexNet was simply classify an image into 1,000 labels among 1,000 labels. So what you do is you feed an image through a convolutional neural net, and then you have a fully connected network at the end, and your job is to basically classify what sort of image this is. Is this a cat? Is this a dog? Or is this a car? And this sort of started the breakthrough in the deep learning revolution. So an object detector sort of evolved from this sort of architectures of using CNNs. So you're going to see CNNs everywhere throughout the slides. So how can you extend the previous problem of classification to not only just classify at an image level, but also at an instance level inside the image, where the specific object is located? So what you're going to do is basically treat the bounding box prediction of the object as a regression problem, as a separate head as with the classification problem. So from the fully connected layer, you have one head that goes to class to predict the class, and one head that predicts the box coordinates. And both of them have separate losses. So the class loss will be a softmax loss, and the regression loss will be an L2 loss. And basically this will be framed as a multitask loss, and it's basically a multitask learning problem essentially. And as we progress through different methods, you will see how multitask objectives are framed for object detection problems, and what are the challenges associated with those. So another common aspect of object detectors is this backbone network. This is usually a giant convolutional neural network. So when AlexNet came out, this was considered pretty deep, but not anymore. And you can pre-train this network on an image classification task and fine-tune it for object detection specifically. So here are some of the examples of backbone architectures which were developed since AlexNet came out. So on the top, you can see ResNet, which stands for residual networks. These are very deep networks, and you can extend them to up to 100 layers. And the reason they work so well and not suffer from vanishing gradient problems is because they have these residual connections that help in backpropagation. Another example is VGG, which is also a modern feature extractor or a backbone network. And some other examples include inception network, exception network, and there are a bunch of different architectures for feature extractions. So in the previous formulation, given an image, you could only find one object or localize the object for one instance only. So what about multiple objects? So the obvious idea that comes to mind is to do a sliding window classification in the image. So what the idea is to basically slide a window across different sections of the image and classify those particular crops. So in this case, is this a dog? No. Is this a cat? No. Is this a background? Yeah. So, and then you just keep sliding the window. So this is a dog. Again, this is the dog. This is a cat. And you quickly see the problem. You need to apply the CNN to this crop. You need to apply the CNN to a large number of crops of various scales and sizes. So this problem becomes quickly very intractable. And this sort of builds leads to the first major method that was developed in object detection called region proposals. So region proposals are basically a way to find out blobby image regions in an image that are likely to contain objects. So they're relatively fast to run, and they sort of gives out lots of image proposals in a few seconds. And the method that is used is called selective search, which is also a classical method, and there is no learning involved. It does some graph-based search to generate these proposals. And using these region proposals, RCNN, which stands for region-based convolutional neural networks, was developed. So given an input image, you first run selective search to generate around 2,000 ROIs. And the next step is to warp this ROIs into a fixed size image, because ConvNets usually have fixed input dimensions. So you have to resize the crops into a fixed dimension before passing it through a ConvNet. And you forward each of these warp regions through the ConvNet, and you classify those crops as the object class. And you also regress a bounding box. So not only do you predict the classification for each crops, but you also adjust the crops to better fit the object. And an obvious problem that arises from this is that what if you generate multiple proposals around the same object, where all of the classifications are the same class? So how do you get the correct bounding box for this car? So the algorithm that is used is called non-maximum suppression, or NMS for short. So the input to the algorithm is a list of proposal boxes and the corresponding confidence scores of those detection, and an overlap threshold. And your output is a filtered list of proposals. So the algorithm is as follows. So you select the first candidate among the proposal boxes with the highest confidence score, and you remove it from the set B. And now you compare that proposal with all other proposals belonging to the same class, and you calculate the overlap, or it's called IOU here. We will get into the details of IOU later on in this talk, but what it means is basically IOU compares the overlap between two bounding boxes. So you choose the bounding box with the highest confidence, you compare it with all other bounding boxes, and if for each bounding box you compare with, if the IOU is greater than some threshold, you remove the proposal from B. If it's not, then you do not remove it, and what that means is basically it's another instance of the same object. And you repeat this process till you eliminate all proposal boxes from the set B, and that will give you the best fit for the current object. So RCNN has a lot of problems. So the first obvious problem is you're feeding 2,000 box proposals through the same ConvNet over and over again. So it takes enormously long time to train. And it also stores a lot of features on disk. And training is slow. It takes around 84 hours to train. And the inference is also slow because during inference time, you're also generating box proposals and you're sort of sequentially feeding them through ConvNet for classification. So this has a lot of problems in terms of time. So in order to improve that, FastRCNN was developed. And what FastRCNN does is basically it uses a ConvNet that is shared for all the region proposals. So what they do is basically they run selective search on the original image, and they transform the proposals generated through the ConvNet into the last feature map of the ConvNet, basically. So what they do is they transform through the ConvNet all the selective search, the proposals to the last feature map, and then they resize those transformed region proposals into a fixed size proposal, and through something called an ROI pooling layer. So it's a differentiable way of resizing and pulling regions of interest from a feature map. The design is kind of complicated and it's not important right now, but the overall idea you should know. And then the pooling layer sends those region proposals to a fully connected layer, and the rest is same. You have two heads, one for softmax classification and one for bounding box regression. Another common theme you'll see in all these object detection methods is like you'll have two losses, one for classification and one for the bounding box. And similarly, you set up a multitask loss, you take the derivative and you backprop end-to-end to update the network. So here's some comparison in terms of training time and test time between RCNN and FastRCNN. SPPNet is another network that sort of comes in between these two methods. It's not important for today. So you see instantly FastRCNN almost reduces training time by 10 times, actually, and which is great. And in test time, you see FastRCNN is really fast compared to RCNN. And what's interesting here is like majority of the time during testing is taken up generating region proposals, which is a classical way of generating proposals. So the next obvious improvement that comes to mind is what if you can learn these region proposals instead of just using some classical way of generating proposals. So came faster RCNN. So this does exactly what the obvious solution is. It has a region proposal network to generate proposals instead of using some sort of classical way of generating proposals. What it does is it jointly trains with 4 losses. So the multitask problem becomes even difficult here. So, and you should note here the classification loss in the proposal network and in the final classification layer is not the same. So this classification loss is basically saying whether a certain proposal has an object inside it or not. So it's a binary classification loss. So it's either a foreground or a background. And the bounding box loss sort of regresses the initial guess of the proposal. And then you feed the initial guesses through this region proposal network through ROI pooling, as same as FastRCNN. And then you fine tune the results by predicting the relevant category of object, and also you refine the bounding box further. So as you can see, FastRCNN achieves order of magnitude improvement over FastRCNN. So it completely reduces, gets rid of the overhead time that was used by selective search. And you'll already see a team developing that that to improve object detectors, you should go fully end-to-end and use convolutional operations as much as you can, because they're fast and highly parallelizable. So you should get rid of any sort of hand design features and sort of train the whole network as much end-to-end as possible without designing handcrafted features. So the next sort of improvement over RCNN and its family of methods was detection without proposal. So the previous methods that you saw were sort of 2-stage methods. You had one region proposal network It was stage 1, and then it went to stage 2 for classification. So it was those methods can be broadly classified as 2-stage methods. What if we can do the whole detection objective through one forward pass and go from input image to a tensor of scores with like one big convolutional neural network? So this is where YOLO or SSD comes in. We'll look at YOLO specifically for this talk. So the algorithm for YOLO is pretty simple to understand, but there are very subtle architectural adjustments happening inside the algorithm. So I'll give you a high overview of what's going on in YOLO. So given an input image, you divide the image into a square grid of any size. So here I'm showing a 7x7 grid. And you set up anchor boxes for each grid. So the anchor boxes sort of represent possible object shapes that can exist within that grid. So every grid has a bunch of anchor boxes, and these anchor boxes are hand designed again. So you're introducing a different hand design element here as well. And you go from an input image of 3 cross H cross W to an output of 7 cross 7 cross 5 times B plus C. So what is 5 times B plus C? So 5 times B plus C is basically 5 comes from these 4 numbers, which are the X and Y location of the top left corner of the bounding box and the height and width of the bounding box, and a confidence score which says what is the likelihood that an object exists in that particular bounding box. And for that bounding box, you also do a one-hot prediction of its class. So that's how 5B plus C comes in the depth of the volume that you predict. And yeah, this is then trained similarly end to end. You have 2 losses coming out of this this depth here. You do an L2 loss on the bounding box, and you do a softmax loss or a cross entropy loss, sorry, on the classification. And so this is sort of has more details on how the YOLO algorithm works. I sort of give you a sort of a overview of how the algorithm works, but I'm just going to skip over these details because they're not they're sort of complicated to understand, and yeah, we have a lot of methods to cover. So if you're interested, the links are up on the website, so you can take a look at the details later on. So YOLO has 3 versions. So this is version 2. The original YOLO was improved upon by making a variety of modifications, but some of the important ones were uses convolutional anchor box prediction rather than predicting bounding box from fully connected layers. So if you look at the architecture of YOLO, it uses convolutional neural net architecture called DARKnet, and then it goes to a fully connected network, and then it predicts the bounding boxes and class scores. But YOLO v2 improves upon that by going fully convolutional up till the end while predicting anchor boxes. So you again see the idea of using convolutional layers as much as you can, just because it is easy to train, and it's fast. And also it improves by not only removing the hand design elements in setting the anchor boxes. What it does is basically it runs k-means clustering on the training data to find good priors on the anchor box dimensions. And after running k-means on the entire data set, it uses the top 5, or I think in YOLO it uses 9 anchor boxes. So it uses the top 9 sort of width and height to generate the anchor boxes for each grid. And it stabilizes training by predicting direct location. So when it does bounding box regression, it restricts the output to be between 0 to 1. So it predicts, you see here, tx, ty, and it predicts the log of the width and the log of the height of the bounding box. So these are just, you know, architectural designs that just stabilizes training. So object detector models are typically huge and very difficult to train. And training can be extremely unstable if you don't design your network to account for all these subtleties. So my goal today is to just give you an overview of these methods. But if you're going to implement an object detector, there are a lot of subtleties that can just like not let you converge while training. So these are the subtleties that improve object detectors under the hood. And YOLO v3 is again an upgrade over YOLO v2. Basically, it does another bunch of modifications, which are very subtle. It does multi-scale prediction. Basically, the idea behind multi-scale prediction is to capture objects of different sizes. So multi-scale, by multi-scale, I mean not predicting from the last layer, but from intermediate layers as well. So to pick up objects of different sizes and scales. It also adds skip layer connection to just improve performance. Yeah, I mean, these are just design choices. You can't really explain why they work so well. So let's look at some of the important object detection metrics that are used for benchmarking these detectors. So I talked about IOU while explaining non-max suppression. So formally, IOU is defined by the intersection of two bounding boxes divided by the union. So this is a metric to measure how close two bounding boxes actually are. And in terms of detection, true positives, detection is a true positive if the following three conditions hold. So if your detection confidence score is greater than some threshold, and your predicted class matches the ground truth class, your predicted bounding box has an IOU greater than some threshold, which is usually 0.5. It's standard, which is accepted over the community. And a false positive is a wrong detection. So a false positive is triggered when either step 2 or step 3 is violated. A false negative is a detection where confidence score is less than the threshold. So violation of 0.1. True negative doesn't apply to object detection because there are a lot of things that you cannot detect, and there are infinite number of things that you cannot detect. So it doesn't make sense to measure true negative. Precision is the sort of measures the accuracy of your object detector. So it's defined as the true positive over true positives plus false positives. Recall is your ability to capture all the relevant objects in an image. So it's defined as true positive by true positive plus false negatives. A common graph that is plotted for object detection is the precision versus recall curve. So by setting the threshold values for confidence scores at different levels, we get different pairs of precision recall. So what happens if you decrease this threshold? So you're more confident in predicting bounding boxes, right? So your recall will increase. So you're capturing more and more objects in the scene. But if your threshold is low, you're more likely to predict wrong things. So your false positives also increase. So sorry, go ahead. Someone say something? Okay, never mind. So yeah, if you reduce the threshold, yeah, your recall should increase, but your precision should go down. And this is a curve that sort of reflects that as you reduce the confidence threshold. But in order to measure performance of an object detector, you need to come up with a number, and that number is called average precision. Average precision is the area under the precision recall curve. So before computing the area, the precision values are interpolated at every recall values to sort of reduce the weakly effect. So when you decrease the confidence threshold, your precision should decrease, but it can also increase. It's not guaranteed to decrease monotonically as recall increases monotonically. So the way that the interpolation is done is basically at every recall level, P interpolated, precision interpolated is the maximum precision that exists for all recall values that are greater than the current recall value. So you sort of draw this boundary around. along the precision recall curve, and then you calculate the area under the curve, and that gives you the average precision for this particular class. So remember, precision recall class curve is generated for a single object class. So a mean average precision is basically taking a mean over all the average precision of all the classes, and that gives you the final accuracy metric. So we now move on to a new detector called RetinaNet. So right now we are still dealing with one-stage detectors. So we talked about RCNN and its variants, which were two-stage detectors. And we talked about YOLO and SSD, which were one-stage detectors. And now we are looking to improve upon the existing YOLO implementations. So RetinaNet introduces a new loss function called the focal loss. So there exists extreme imbalance between background that contains no object and foreground that holds objects of interest during training. So in a training set, in an image, you'll probably have one object or one annotation of a bounding box, but the rest of the image will be sort of empty. So focal loss is designed to assign more weights on harder and easily misclassified examples. So like background with noise, texture, or partial objects can be easily misclassified. And is designed to downweight easy examples. So like obvious backgrounds, just say like the sky or some like grass, for example, which can be obviously an empty background. So what it does is basically, so this is the normal cross entropy loss for binary classification. You can reformulate this formula by writing CEPT. So PT can be, by the way, Y is the ground truth binary label here, and P is the probability that the box contains an object, right? So this is the cross entropy loss. And you can reformulate the cross entropy loss as minus log of PT. And so easily classified examples will have large PT. So that is when P is very close to 0, when Y is 0. So if you put Y equals 0 here, you have minus log of 1 minus P. So if P is close to Y, then P should be also close to 0. So what you can see on the graph over here is that for objects that you have high probability, you can also incur significant loss here. So what this focal loss does is sort of downweights the loss value for well-classified examples by introducing this term right here, minus 1 minus PD to the power gamma, where gamma is, again, a hyperparameter that needs tuning. So I believe in RetinaNet, they use gamma equals 2. And that sort of reduces the loss quite a bit for objects which are well classified. The second thing that RetinaNet does is it incorporates a feature pyramid network. So a feature pyramid network is basically an extension, a convolutional extension of image pyramids in the classical sense. So you have the traditional bottom-up pathway, which goes through various stages. And one more thing you will notice in sort of backbone architectures of object detectors is a human bias in terms of design. So you always start with high spatial dimensions and low feature dimensions, and you reduce the spatial dimensions and increase the feature dimensions as you go down. So the reasoning behind this is like the early layers are supposed to capture more finer details such as edges and gradients and all that sort of stuff. And the later layers is supposed to capture more information, more global information about the image, such as what sort of category or what objects are contained in the image and all that stuff. So the idea behind feature pyramid networks is basically to do prediction at all scales. So and each scale has a different prediction head. Basically, so at the layer C4, you will predict one set of bounding boxes and one set of classification scores for those bounding boxes. And and the bounding boxes will have different scales during prediction. And the way that this is designed is basically you go from the bottom up, you reduce the spatial dimensions, and you also have a top-down pathway where you go from lower spatial dimension to higher spatial dimension. And you also add these lateral collections here so that during upsampling, you do not lose information. And this is the full architecture of the of RetinaNet. So you have a standard ResNet model as its backbone. You stick a feature pyramid network on top of that, and at each feature level, you predict class and bounding boxes. So in this paper, usually in YOLO, you would go from here to and you would predict the bounding box and classification directly, but what they do in this paper is basically they have different subnetworks for prediction of bounding boxes and classification. So they apply the focal loss for the classification here, and they apply the L2 loss for the bounding box. And so now we move on to a method that sort of gets rid of some of the hand design features, or like one major hand design features, which is anchor boxes. So even RetinaNet used anchor boxes here. So you see the dimension here, W cross H cross KA. So K is the number of classes and A is the number of anchor boxes. So it still relies on anchor boxes for prediction, and anchor boxes are sort of hand design features, and it can sort of vary your performance of your model based on how you choose your anchor boxes. So CornerNet was the first paper that sort of got rid of the anchor boxes, and what they sort of framed the object detection problem very differently. They framed it as detecting paired key points. So bounding box can be thought of as a top left key point and a bottom right key point. So they still have a backbone network, but what they do instead is they predict heat maps of top left corners and bottom right corners. And they also predict embeddings of those corners. So the embeddings are supposed to contain information about the object of which the top left corner is being predicted. So here's again some of the drawbacks of using anchor boxes. So typically when you design anchor boxes, you should have lots of scales and lots of sizes to ensure that at least one of the anchor box covers the actual object, if there is one. And actually, during training, a tiny fraction of anchors are positive examples. And so when you do backpropagation, you only pass gradients to the anchor box that fits the current object with the highest IOU. So you do not train the other anchor boxes. So what it does is basically slows down training. So you need lots and lots of examples to train all the anchor boxes properly. And it adds extra hyperparameters, which needs tuning. And as more and more hyperparameters make your model more and more complex, and object detector models are typically very huge, and that makes the problem really harder. So the goal is to reduce as much hand design features as possible and create an end-to-end network that can go from image to a prediction. So let's take a closer look at how CornerNet does the prediction of the corners and embeddings. So it has two prediction heat maps, one for the top left corner and one for the bottom right corner. So what it does is it first checks if this is the top left corner. Okay, if it is, then what class is it and who's top left? So the embedding layer predicts that which object does it belong to. So here it belongs to this object's top left corner. Similarly, for the bottom pyramid, heat map, it also predicts the same class and who's bottom right. So it also predicts the embedding vector, and then they sort of match the embedding vectors of the top left and the bottom right to finally generate the bounding box. And the way they train this network, or they train the embeddings to reflect the same objects, is by using two losses, L pull and L push. So what the pull loss does is basically it sort of brings these two embeddings closer together. So ETK is basically the top corner of class K, and EBK is the bottom corner of class K, and EK is like the mean of ETK. So it's EK is basically ETK plus EBK by 2. And it sets up this loss to bring those embedding vectors closer together. And for every other embedding vectors that this heat map produces, it does a push loss to push those embedding vectors away. So it's essentially learning a metric of the instance of the object while predicting. So this is how it sort of groups the two key points for prediction. So one possible problem that can arise for CornerNet is, say, consider this tennis player, I think it's Sharapova. While if you're predicting this object, the top left corner has almost no local information about the object. So how can you use features to predict this object? So they use something called corner pooling, which is a really interesting way of sort of getting information from the right and the bottom of the top left corner. So what corner pooling does is basically it looks all the way to the right and it pools features. It does a max pooling essentially to pool the most important feature all the way to the right. And it also does a max pooling all the way down for the top left corner. Similarly, you have a corner pooling for the bottom right corner. It goes all the way up for max pooling and goes all the way left to get the max pool features. And then it sort of adds these max pooling layers to before it feeds to the prediction networks for the heat maps. So here's the full architecture of CornerNet. So you see the corner pooling happens after the image gets passed through the backbone network, and then it goes through the heat map layers for predicting the corners, classes, and embeddings. CornerNet also uses a novel architecture called the hourglass network. So most of the object detectors that you saw now use the design bias that I was talking about, which was downsampling as you go deeper. So they claim that this hourglass network is very crucial to the improved performance of CornerNet. That is because the layer goes, the backbone downsamples, upsamples multiple times, essentially going through bottlenecks. What they're doing by, what they're generating by doing this is they're capturing, or at least they claim, there's no quantifiable way to, or evidence to show this, but they claim that this network sort of captures both global and local information in one unified structure. So once again, you see an innovation to get rid of sort of hand-designed multi-scale prediction networks to sort of capture all the local and global features in one network. So the multi-scale predictions that you saw previously sort of was another sort of inductive design bias because predicting from earlier layers would capture different scales of objects and rather than predicting from later layers. So the hourglass network sort of combines all of those features into one. At least that is what they claim. And they seem to have like good results, essentially. So they do pretty well compared against the one-stage detectors. By the way, this metric is mean average precision that I talked about. The two-stage methods are typically more accurate than one-stage methods, but they're also slower. So one-stage methods are faster, but they're sort of less accurate than two-stage methods. But CornerNet sort of reaches this benchmark of 45% mean average precision here. And then they also show the effect of corner pooling. Although like the AP difference isn't much, but it seems to increase with corner pooling, which is expected. So the next method that we'll look at is called DETR. So this is a completely new shift in paradigm in object detection. So the main contribution of this paper is an architecture that predicts a set of objects in a single pass. So this is also a one-stage network. But what it uses is a transformer. So transformers are sort of the new new thing in machine learning. It's basically taken over the NLP community, and it's sort of revolutionized sequence prediction. And LSTMs are no longer sort of used anymore, and transformers are used for any sort of language modeling task. And it's slowly sort of entering the computer vision community as well. So this is sort of the first paper in object detections that uses transformers. So transformers are built using something called self-attention or attention mechanism. So something that Chen talked about in his graph learning tutorial. So the idea behind attention is to, given a sequence, uh, it sort of weighs how you should take in, which input you should focus on in your given sequence. That's sort of the high level idea of attention. The details are sort of complicated, so I'm not gonna cover that in this lecture today. But that's sort of the high level idea. And the great thing about this method is it gets rid of two human designed features or handcrafted features. First, it doesn't need any bounding box prediction. It doesn't need any anchor boxes for prediction, and it also gets rid of non-max suppression. So since you don't have anchor boxes, you don't need to do non-max suppression while you predict. So and it also does set prediction, which is also sort of gaining momentum in machine learning nowadays. Instead of predicting fixed number of objects, you can predict variable objects. But it's sort of not possible to predict variable objects. You have to sort of parameterize a set using some parameters. So a typical way of parameterizing a set would be the cardinality, number of objects in the set, et cetera, et cetera. So it uses a unique algorithm called the Hungarian algorithm for bipartite matching. And it sort of assigns the predicted object to the ground truth object in a one-to-one fashion. Yeah. And this is sort of the architecture that is used in transformers. So given some image features, it goes through a bunch of multi-head self-attention layers. This is the encoder network. And then you have a bunch of object queries. So you can think of the object queries as where to look inside the image. You're querying inside the image to probe where possible objects can be. So that goes into the decoder. It also uses multi-head self-attention. So, and then finally it goes through feed-forward networks to predict class and bounding box. This is sort of hard to understand right now because transformers are kind of complicated in understanding, but they surprisingly work really well. And here's some qualitative results for DETR. Like you can. This graphic shows the visualization of the attention maps, especially the last encoder layer for a set of reference points. So for this animal here, for this particular point right here, you can see the self-attention sort of captures only the relevant parts very accurately and can distinguish between this object, this animal over here pretty well, although those seem to be together. And similarly, you can see the attention that's being applied is actually sort of semantically makes sense while doing prediction. Similarly, for this object, it's looking towards the right, the edge of the image. So visually, it sort of makes sense that the attention mechanism actually is able to distinguish instances of objects pretty well. Another result that you see here is the visualization of the box predictions from the COCO dataset. So COCO is one of the standard object detection datasets. And DETR has 100 prediction slots, so it can predict, you can set this to as much as you want. So you assume like max you can only predict 100 objects in an image. So these are some of the decoder slots, or you can think of these as the people responsible for detecting particular objects. So, so each box prediction in this COCO dataset is represented as a point with the coordinates of a center in a 1x1 square normalized by each image. So basically, if you normalize each image into 1x1, then these points refer to the center coordinate of the object. And the points are color coded so that the green color represents the small boxes uh, uh, and red to large horizontal boxes and blue to large vertical boxes. So we observe that each slot sort of specializes on certain areas and box sizes with several operating modes. So you see like this slot sort of learns to predict green type objects on the left hand side, and these sort of learn the green type on the right hand side, and each sort of specializes on a particular area of the image to focus on while predicting objects. And this can be related to the attention mechanism. So these slots are paying attention to specific parts of the image while predicting objects. So in terms of visually explaining, it's pretty fascinating. And finally, some quantitative results on DETR. You can see the naive or DETR with the ResNet 50 as its backbone has an AP which is comparable to faster RCNN, which is a two-stage method, and DETR is a one-stage method. It does pretty well in terms of AP comparison, but it's significantly faster than in terms of speed compared to two-stage methods such as faster RCNN. The problem with DETR is that it doesn't do too well on small objects. So APS denotes the average precision for small objects, and it sort of suffers for small objects. They haven't explained in their paper why the method sort of not picks up don't pick up small objects so well. But overall, in terms of accuracy, it's pretty good and it's pretty fast, and that's the reason being is because the network is all end-to-end. There is very little hand-tuned features that go into DETR, and the prediction is done completely end-to-end. And that's the result of it's learning completely from data, and that's why it does so well and so fast. So in summary, I've presented two-stage methods, one-stage methods, and then SIT prediction. So under two-stage methods, you have RCNN, the family of RCNN, where you have you first generate region proposals, and then you refine the region proposals through some pooling and convolutional layers to finally predict the class and location. These methods have handcrafted elements, such as anchor boxes and non-max suppression. They're more accurate than one-stage methods, but typically are slow. One-stage methods include YOLO, SSD, RetinaNet, CornerNet, etc. They also have handcrafted elements such as anchor boxes and non-max suppression. By the way, for two-stage methods, only faster RCNN has anchor boxes. The other two don't. Their one-stage methods are less accurate than two-stage methods, but they're faster. And CornerNet is an exception in one-stage method that gets rid of anchor boxes. And then this is the modern paradigm or modern design and the paradigm shifting object detection, which uses set prediction. So right now only DETR is the method that does it, and it doesn't have any handcrafted elements, and it is fast and comparable in terms of accuracy with two-stage methods. So that is it in terms of some of the object detectors that have been developed since AlexNet came out. And yeah, we are good to go for our first tutorial. I think this link is on the website as well. So if you go to the website, darlab.org/summer2020, you will have the link to this repo. It's a Google Colab. There is no coding involved in this. This tutorial basically shows you how you can use a pre-trained object detector in TensorFlow 2.2 to perform inference. You can choose to experiment with two object detectors, SSD, which is a one-stage method, and faster RCNN, which is a two-stage method. Just follow these steps to connect to Colab, and you can read the instructions in the notebook and execute sequentially. You are expected to finish this in 10 minutes. It's really quick. It's really small. You just have to run a bunch of code to see the outputs. And I think after this, Andrew is gonna take over.
So the next thing we're going to talk about briefly is what I like to call inference platform tools. Um, so uh, so what is the problem, right? So a lot of different hardware and different platforms have specialized hardware, both for inference and like computer vision and matrix operations. So say you develop your network, you develop your object detector. You want to be able to run this like on your drone. You want to be able to run this on your dev machine. You want to be able to run this on a lot of different platforms, and you want to have as fast of a speed as possible. Um, but so a lot of these large general purpose frameworks like PyTorch, TensorFlow, etc., they try to target a general audience. So like an x86 processor plus CUDA, aka an NVIDIA GPU, to ensure their code can run on as much hardware as possible. Now, when they come up with their different versions, they'll compile with a lot of optimizations, but those optimizations are more of like, okay, we're targeting this range of Intel CPUs, and they all have like these specific vector operations, for example. And so, and a lot of times too, the versions that you'll get that you don't compile yourself sometimes won't have all of the optimizations turned on. A lot of work has been done on building specialized forks for running on embedded and mobile hardware. And these are like light versions, but a lot of times this is less of like optimizing it for hardware and more of either like reducing the precision or reducing like the size or the complicatedness of the network. An example would be like you know a network that's optimized for like mobile phones, for example. So the solution to this problem is there's these inference engines that are optimized runtimes for a specific set of hardware. And these engines can make better use of dedicated hardware because they're specifically targeted for a specific vendor's hardware, specific devices. So examples of like this dedicated hardware might be like, vectorized engines on CPUs, might be your integrated CPU, in like, say like an Intel CPU, for example. There might be additional specialized accelerators that are designed for running deep learning operations, as well as additional like accelerators like an FPGA, et cetera, et cetera, et cetera. Additionally, these networks, these tools will optimize the instructions for use on to use specialized CPU or GPU operations. So like using vector operations, for example. And also what's nice about a lot of these is specifically OpenVino, which is one of the ones I'm going to talk about, is that it can use this heterogeneous compute model, meaning you can run it on the CPU or an Intel FPGA or an integrated GPU, which lets you basically like at runtime, say, okay, I'm going to change my model to, or so when I start up inference, I can say I'm going to use the CPU now, maybe because I'm running on something where I can afford to use more CPU resources, or no, I need to only be able to run on like the integrated GPU, for example, on my like Intel NOC that's on my drone. And so then I force OpenVino to use the integrated GPU, or I might have like what's called a Movidius USB. It basically looks like a USB thumb drive, but it lets you do accelerated inference. So a little more specifically about OpenVino. So it's basically an accelerated vision inference engine and optimizer. So it's specifically designed for object detection and other deep learning vision tasks. It optimizes the inference on Intel products specifically. So you have Intel CPUs, integrated graphics, there's FPGAs you can run it on, and an embedded accelerators. So that's like the Movidius stick that I was talking about. And there's been some frameworks done of like running like TensorFlow Keras versus OpenVino on the CPU, and you can get up to like over or beyond like over 3 times speed up. There's different networks and different architectures will have like different amounts of speed up. It also depends on how you install TensorFlow or Keras, or like did you use the provided like binaries, or did you compile it your own with like specific optimizations or whatever. So I think the bigger thing that OpenVino provides is, one, you don't have to compile TensorFlow yourself with specific optimizations to try to squeeze out an extra 10, 20, 30%. You can just download OpenVino, run your run your model through their scripts to optimize it, and then run it on your Intel hardware, for example, and get this 3 times speed up. It's basically for free after you just spend a little bit of work optimizing your network. And the other thing that it gives you is that you can now run it on different hardware. You're not limited to using your CPU or your or like you need to get an NVIDIA GPU. No, you can run it on your integrated graphics. You can get an FPGA, or you can have like a Raspberry Pi and plug in this NVIDIA stick and run it on the Raspberry Pi, and it'll use the NVIDIA stick to do inference, for example. So that's what's really nice, is the flexibility as well. So what's also nice is that it doesn't just accelerate inference for like say like TensorFlow or Keras or whatever, like these types of models, but it also has some optimized versions of OpenCV and OpenCV's like deep neural network like backbones and stuff. And so this in the optimized version of OpenCV, like general OpenCV stuff, like traditional CV stuff, is really just a version of OpenCV compiled specifically for Intel hardware with certain optimizations turned on. So you don't get a huge speed up here, but in terms of the deep neural network backbone, you do get a huge speed up. What's also nice about OpenVino is that it's very easy to switch the precision, and that can give you additional speed ups as well. So how does this work? Is so you train you come up with your architecture, you have your model, and you do everything normally in like Caffe, TensorFlow, whatever. There's multiple different models you can do. So you do all that stuff normally, and then you take your model, and there's some scripts that you run that converts that model to an intermediate representation. And OpenVino's inference engine can basically read this intermediate representation and run your model. And so this intermediate representation is based off of the network topology, the weights and the biases. And so you basically take your model, you save it, you freeze it, whatever. You run it through OpenVino's scripts, and then they output, it's like a .bin .xml file, and then you can basically just run it then through OpenVino. So OpenVino also does a lot of additional optimizations as well. So it'll merge group convolutions, fuse different layers and whatnot. So it really helps to really optimize your network to be able to get the most performance out of it as possible. So all of this is, so far we've talked about OpenVino, which is on Intel hardware. There's also another thing called TensorRT. It's sort of the equivalent of OpenVino, and the way NVIDIA markets it is basically lets you run your like specialized accelerated networks on everything from like their most powerful like GPU servers to like a Jetson Nano. So when you so in TensorRT, you can choose like the target device, and it will it'll make special optimizations and choose specific kernels, et cetera, and use specialized hardware. And you could tell it to also use specialized hardware for the specific devices. And then again, it just performs like additional optimizations and whatnot for the specific targeted NVIDIA hardware. And then you can learn more by going to the dev website. And I also put together some resources here. And there's two things in specific I wanted to show. I think I need to share my screen again. Okay, so first, if you're using OpenVino, for MBZ, we've developed Docker files to be able to run OpenVino. This is a little bit of a work in progress right now. It's still using Kinetic because that's what we use for MBZ. But this will get updated and improved upon in future versions. And the other thing I wanted to talk about was specifically just sort of like show what the difference is between like a normal inference and OpenVino inference. So this is what we used for MBZ. We used OpenVino. So like your model, for example, is, so we use tiny YOLO v3. So you have like a .bin.xml. This is what OpenVino reads. And so then you see we have like multiple different models. And then specifically, you can check this out on your own time as well. You can choose like the target device. So we chose like the GPU. You tell it, you know, where your plugin is. If you do some extra stuff, you tell it like where the model is. You load the model, and then to actually run, you just tell it to infer, and then you get your output, and you can do all your other stuff. So feel free to check this out and get an idea of how you can use. So in this specific case, tiny YOLO with OpenVino. YOLO is a special case when dealing with OpenVino because YOLO isn't uses darknet, and because of that, you have to first convert from darknet to TensorFlow, or you can use a TensorFlow implementation if you want. We also, so Lorenz last summer put together this really nice repo, and he talks about like how to train and stuff for both TensorFlow as well as OpenVino. And then there's also additional docs here on converting a YOLO model to an intermediate representation. So first you have to convert YOLO to TensorFlow, and then you just, you know, convert the weights and whatnot. So first you have to convert to TensorFlow, then to the intermediate representation from darknet. So that's all I had for this. Did anyone have any questions?
So yeah, I'll just be going over a pretty quick introduction to some of the really popular object tracking methods. And basically the three that I go over, which are correlation filters, including the MOSSE tracker, then median flow tracker, and the tracking learning detection, or TLD tracker, they kind of go over three different type of frameworks or like algorithms that are pretty different from each other for kind of tackling this problem. And a lot of the other popular methods like KCF, CSRT are correlation filter based. So what I talk about in regards to correlation filters and MOSSE can also be applied to those with some modifications. All right, so what is object tracking? You can see in this video of cars moving across the screen, they did a really simple object detection just for cars for this particular application, and then used tracking throughout the entire scene as the car moves across the image. And because you get a smooth bounding box, because you're using object tracking, you can estimate certain things about the object itself. So for example, in this, on the top of the image, you can see that they're estimating the car speed. And so the smooth bounding box motion allows you to estimate those kinds of things. And you can see that the object tracker maintains its bounding box around the object, even though the car is partially occluded by the white fence in the yard, and also is a changing background from yellows, greens to browns, etc. And then here's another example of object tracking where you're tracking multiple objects in the same scene. And you can see on the left, for example, the two people running in image space pretty close to each other. Those are being tracked together. So there are some artifacts like that that I'll talk about as well. And so object tracking sometimes makes up for what lacks in robust object detection. So for example, robust object detection, which usually nowadays composes of deep learning methods, can be expensive in both computation and time. So it takes like a GPU or a lot of computation power as well as time. So the frame rate might not be in real time, or you might miss frames. And so tracking can make up for those things and fill in the gaps. So here, if you see a timeline with each red line basically being each point you get a detection, say you get it like once a second or 5 times a second, and you get a detection at each of these points, you can make up for the gaps in between by reinitializing your tracker. This is one very simple way of doing it. Reinitializing your tracker at each of these red points where you get a new detection, and then track for maybe a quarter of a second or a full second until you get the next detection. And then you can, whenever you arrive at this point, for example, where you have your tracked frame, immediately when you get the new detection, you can compare that tracked frame to the new detection and combine the results by using some intersection of reunion or some other error metric to get the best result. And so smooth object tracking is useful for inputting feasible inputs into controllers for following or tracking objects in your scene. So for example, if you're flying or driving your robot towards some object through visual servoing, for example, then having a smooth track on that object would be very helpful. And as I mentioned in the first video that I showed, state estimation of the objects in the scene is another use case, and there are other uses as well. And in this presentation, I'm just focusing on single object tracking. So the image, the GIF where I showed multiple humans being tracked during the race, I won't be covering multi-object tracking because there you have to take care of maintaining different object identification markers and distinguishing from them as they cross in the scene. I'll also only be talking about monocular camera images as opposed to LiDAR, so like using 3D point clouds for tracking, having stereo camera or depth information. And as I mentioned, I'll just be going over these 3 trackers, which cover 3 pretty important ways of doing tracking. So first off, we'll talk about correlation filters. Correlation filters are pretty useful for finding similar regions in an image given some initial filter or a template, which you can convolve over the entire image and then see where you get a peak. So for example, on the right side, you can see a few different, a few different convolution operations done over the image using some filter. The filter is this middle row right here, applied on the top image seen here. And, or sorry. The middle row is after the filter is applied. The filter, they're looking for this red square right here. And so you can see that a naive approach results in some peak where the solution is found with some noise around that peak, and other methods, these popular correlation filter tracking methods have much sharper peak, and then as does MOSSE, which I'll talk about. And so you can see that the peak side lobe ratio is not as high here as it is in the other examples. And so UMACE and ASEF rely on offline training for generating filters, whereas MOSSE does online training with a few different images in order to hone the filter down to something that would result in a very high peak to side lobe ratio. And MOSSE stands for minimum output sum of squared error. I'll go over the process that they use to generate the filter, which involves this optimization problem. So these slides I borrowed from Professor Simon Lucy at CMU. He teaches a computer vision course. And this is how correlation filters are generally used to find a similar area in an image for tracking an object. Let's say you have this picture, I think it's the Tasmanian devil, and you're trying to track the face of the animal. You have a known signal, which is this input image, and you know that you want your response after you apply some unknown filter to have this very strong peak in the center of your bounding box. And you need to find this filter that results in this so that you can use the filter in future frames to find the location of the object. And what MOSSE does is that it, as opposed to the other correlation filter methods I mentioned, it uses online filter generation to generate this filter. And it does it in much faster than real time as well. And it, so the way that it does this is it solves this optimization problem by minimizing a sum of squared error, or SSE, between a hypothesis filter on image convolution and the desired output of the convolution, which is this strong peak that you see right here. And this is a direct quote taken from the paper. So the filters are constructed during initialization, which is as opposed to the offline methods that were done before this paper. And basically they take the bounding box input, they apply some random affine transformations to generate some copies with small perturbations, and then use that to generate the filters. And so the tracking step itself is done in the Fourier domain because using FFTs is pretty fast. And so you can accomplish tracking by doing these operations in the Fourier domain. So you take the FFT of the image, do an element-wise multiplication with the FFT of the filter, which is, you can see here, the image, filter, and the output. And then when you get the output, you just do the inverse FFT of that, and then you get this correlation field, which is the peak where you this correlation field, signal peak there. So there's an example correlation output after you do the inverse FFT. And so you can see the main peak is here, and I don't know if it shows up pretty well, but there are some side lobes here and here, for example, just surrounding the main peak. And even within this main peak square, actually, there's some side lobe. But the side lobe, peak to side lobe ratio is computed like this, where you have the maximum value within the peak, and then the mean and standard deviation of the side lobes, which you use to generate this ratio. And you can see that using this MOSSE filter is pretty effective if you're tracking this this part of someone's face, for example. There's some issue whenever you have some out of plane rotation caused by this guy turning his head, or the camera turning around the guy. And then you can see that it starts tracking some part under his eye here. Because it doesn't make up for changes in appearance of the bounding box or any kind of scale variation, basically. And on the right, you can see more detailed information. So you have this entire input of this frame, and then the filter that it generates by taking this frame creating some perturbations on that, and then generating the filters here. And then here's the peak correlation field you can see. And here's some more evaluation information. So you can see that whenever you use MOSSE, which is just based on correlation filters and performing the IFFT on an image and a filter, the IFFT, you get a huge frame rate, so almost 700 FPS compared to some of the previous methods, which sometimes relied on offline filter generation and stuff like that. And you can see that this is actually done on a pretty old computer as well. One example where MOSSE did okay compared to some of the previous methods is in occlusion. So basically the framework that they have in MOSSE is that they pause the tracker and resume it whenever there's significant error between the current frame and whatever the initial frame was. And so as long as the object is in, like, after the occlusion is taken away, the object is has a relatively similar appearance, so that it can regain the track. And you can see that whenever the subject turns his head, for example, in this rotation on the bottom right, that the bounding box is not exactly on his face anymore. So it doesn't deal completely well with rotation. And these are some comparisons between a few different correlation filter methods. So I just talked about MOSSE, which runs extremely fast, and that's its main contribution, I guess, nowadays to the field of object tracking. Another popular method, which is used quite often, is a kernelized correlation filter. It's pretty accurate, but it has some false positives, so depending on your application, you might not be able to use it. But it also runs pretty quickly. On a modern CPU, you can get much faster than real time. And then another popular method which we used for MBZ, for example, is CSRT. And it adapts really well to changes in appearance of the object. So rotation, even scale variation, it's really good. And on a modern CPU, it can achieve pretty much real time, but anything less than a very fast CPU, it might not get quite real time. And this is an overview of the CSRT method. It takes the spatial map and then tries to figure out where in the initial frame are the most useful features to track, and then adjusts that over time. But I won't be going over KCF and CSRT here. Okay, so one issue with object tracking is that there can be a failure case where you might be tracking subject A, but then subject B in the scene overlaps onto subject A, and then the bounding box just starts tracking subject B instead. So good failure detection is really important over a variety of scenarios. And median flow was one of the first good failure detections for object tracking. You can see, for example, here, the biker overlaps with this girl, and then the bounding box just drifts on there and then gets stuck to a wall and moves a little bit with other passersby. And so being able to detect if you're no longer on the original object is really important, because then you can ping your object detector, for example. So median flow relies on a backward-forward consistency assumption, which basically means that if you have time 0 and then you track forward in time as you get more of the video stream, that result should be the same as if you start from the future time and then track backwards back to time 0. You should get the same trajectory of your object in your scene. And that's depicted here from an image taken from the paper, where you can start here basically at xt, and then track forward in time to a certain point at t plus k right here, and then you track backwards to the same time t, and then this difference in position in the original frame is some forward-backward error, which they use to determine if the track was successful or not. I have another graphic here explaining that, but I don't think that's necessary. And then they use that error method to generate a tracker that is robust, or at least it is able to detect failure detection. So first, they have the initial bounding box over an object. They initialize some points to a grid over that entire object. Then they use some other tracker like Lucas Canade tracker in the paper's example, and track forward in time. Whatever points that are tracked and result in a forward-backward error under some threshold, they maintain those points. And so that's the filtering out outlier step. And then they update the bounding box around those points as appropriate. Yeah, so they use the remaining points to generate the bounding box. And the bounding box displacement from one frame to the next is performed using the median over the each spatial dimension maximally. And then this other method, tracking learner detection, attempts to continuously improve the tracker over time as we're exposed to different angles on the object and changes in appearance of the object. And so it specifically aims to tackle long-term tracking, which is difficult because there are changes in appearance of the object. And so this is a direct quote from the paper that a successful long-term tracker should handle scale and illumination changes, background clutter, partial occlusions, and operate in real time, which is different than most other trackers up to this point. So for example, like KCF, MOSSE, like these cannot deal with changes in appearance. It also suggests that neither tracking nor detection can individually solve this task. And so it introduces PN learning, which focuses on recognizing misdetections and recognizing false alarms. So basically false positives and false negatives during the tracking process and improving the filter that it's using, wireless tracking. So it has this flow chart between tracking, learning, and detection, where the tracking step is just like any of the other trackers. It estimates the object motion between subsequent frames, but it's likely, or it's subject to fail or never recover if the object moves out of frame, for example, or if there's any large motion, then it might also fail in that case. And so it passes these pieces of the trajectory in the image frame to the learning portion. It has an input from the detection, the reinitialization. So each new frame from the detector goes into the tracker, just like any detector. It scans the full image to localize the object in the frame. And learner gets input from both the tracker and the detector to generate training examples to avoid additional errors. So it basically takes in the input from the detector and uses that as, generates training data based on the errors that it has made and inputs that into the detector to improve it for better reinitialization of the tracker next time. And this is a really important example from the TLD paper where it's initially given the single bounding box of a blurry motorcyclist. And over time, you can see that it adapts to differences in appearance, where it gets higher resolution captures of the biker's jacket and the bike. And in this frame, the red dot signifies that the object is no longer in frame and is able to still make up for that and recognize the object in future frames. Here's a short video of the TLD tracker in action. So you can see that he makes changes in appearance to the object and it still is able to recognize it, even if another object is in frame. And on the right and left sides of the image, you can see that the some of the frames that the PN experts are using to train the detector even better. And this is running in close to real time. It's like 20 FPS. But on a modern CPU, this will run in real time for sure. So I wanted to also bring up a specific method that I mentioned back in April during a lab meeting, which was used for tracking moving objects from a monocular camera image from a UAV. And the specific method focuses on using static points in consecutive images to determine the ego motion or the motion of the camera in the scene, and then uses differences between optical flow calculations to determine pixels that belong to dynamic objects, and then track those dynamic objects through the scene. For the optical flow, it uses a reduced set of fast features, and the real optical flow is computed using iterative Lucas-Kanade method. Yeah, so just really quickly, it has an artificial optical flow, which is computed using homographies between consecutive frames to determine some background movement generally in the scene. And then this real optical flow is using fast features. And because it's using specific features in the scene, it can catch specific objects that are moving not in the direction of the image frame. And so whenever you superpose these, you can see that there's some groups that signify some moving objects. And then you can see some outliers here as well. Yeah. So the outliers are these green arrows, and then you can cluster together these groups of vectors, and they use k-means clustering to do this. Just some details about the hardware. And you can see in action, for example, the superposition of the two optical flow fields. You can see that there's a moving person here, which is captured in the scene, and also captures some of the shadow. And so the shadow is actually captured by the system, and that's an erroneous detection. But it's able to track people moving in the scene that are moving separate from the ego motion of the camera itself. So one particular failure case might be where the subject is moving similar to the ego motion. Yeah, so I just went over a few different methods, and there are many more object trackers here. The ones that I mentioned, specifically MOSSE, medium flow, and TLD, are all implemented in the OpenCV library. KCF, CSRT, these are also in the library, as well as some more involved ones like GoTurn, which is deep learning based. So certain trackers are better at handling occlusions or fast movement, whereas otherwise can adapt to appearance changes. So generally, KCF and CSRT are really popular. CSRT adapts to changes very well, but has a pretty high computation. You can still achieve real time, like 30 FPS, but you have to have a pretty good CPU for that. TLD, because it learns over time, works well under occlusion and also with appearance changes. MOSSE is really good for extremely high FPS because you can get like around 1000 FPS. You can generate different detections and then double check tracking or detections by using MOSSE between frames because it's much faster in real time. Another important note is that performance of these trackers often vary based on how the tracker is weaved into the system itself. So how you weave it into the reinitialization with the object detector, for example, and how good your controllers are on your camera motion, for example, because very fast changes in appearance or fast motions of the object in your image frame can ruin trackers. And so some of the ones that I didn't mention are GoTurn, which is deep learning based, other Kalman filter-based trackers, and also boosting, which is an out-of-boost based tracker. And I think that's it. Yeah, that's all for me. Are there any questions?
Can you go back a few slides to the k-means?
Oh yeah, sure.
How do you pick how do you pick k?
I think they just did that empirically. Yeah.
Does that struggle if there's like more moving objects?
Right, yeah, so if there's more, objects in the scene, I guess you would want a higher k value, but it depends on your use case, I guess.
Okay.
Yeah. All right, let's see. So next we have Andrew's tutorial on tracking. Andrew?
Yep, yeah, sorry. If you guys had downloaded everything, you should have this tracker tutorial workspace. As Brady pointed out, I forgot to also mention that you need ROS vision messages, just so you can view the output. The way the setup works is so here. Let me just go through the whole thing. So you want a ROS core, and you also want to start RTT image view just so you can see the output. And then this is all you need to run on your host. So when I refer to your host, I mean your actual computer. And then when I say and then you just need to run this script right here, this run tracker script. The first time you run it, there will be like errors popped up. Ignore that. All I'm doing is just checking to see if the container name already exists, and if it does, just removes it. So as long as you don't have any containers named tracker dev on your computer, you should be fine. And then the first time you run it too, your build and your devel folders might be missing. That's because the way this works is the Docker container, or the script will mount your entire workspace inside the Docker container. So this is nice because then you can change things locally on your computer, or you can like add new video files, for example, to test with. And then because it's mounted inside the container, all of that data will automatically show up. But the first time you mount it, when you clone the workspace, you don't have these folders. When you mount it, it overwrites the build and devel inside the container, so you might not have those the first time. And so then you just need to do a cac build and then source just like do this basically. Just run cac build and then resource. Okay. And then to actually run the demo, you just need to do cross launch of these trackers, tutorial.launch. And then there's this launch argument that is just test number. So if like say you wanted to have multiple different videos you want to test on, you could just say test 1, test 2, test 3, test 4, and then that just tells you which video to use. Okay, and then launch it here. And then what you see here is the output of the tracker. So this is running with CSRT. So I have a script that will set the initial bounding box. If you want to add more videos, you have to modify that script to specify what the initial bounding box is, and I'll show you how to do that. But this is just kind of to show the magic of CSRT. So if you notice, when it goes behind the pole, it handles that occlusion just well. It also handles this changing background, motion blur. It's very cluttered background. There's a lot of yellow things, you know, and it works perfectly fine. And so the video has ended. That's why it stopped. So it just kind of just shows the performance of CSRT. It was able to track the ball the whole way through. If you want to see how other trackers perform, you can come in here, and I just updated this to have all these other trackers here for you, so you can just comment these out, like so. So now we'll try KCF, and then we'll launch that again. So if you notice right off the bat, KCF isn't really handling the scale super well. As I get closer with the video, the bounding box isn't really scaling super well. At one point it was too small, now it's slightly too big. Versus CSRT was a little bit closer the whole time. If you notice there, it lost the track and then it regained it after it went behind the thing. But then the second time, it just completely lost it. It wasn't able to pick it up after the second time it went behind the pole. And then you can go through and you can play with the other trackers as well. So you can test like MOSSE and whatnot. The other thing to be aware of, these are all the OpenCV implementations. So there might be other implementations that work better or worse or whatever. So if you can see, like MOSSE immediately lost it and then thought the solar panel over there was it, and then it caught onto the pole, and now it's caught onto some random spot. So it's not doing super well with this very cluttered background. It's it's picking up on different areas, and then now it's just going to completely lose it because it thinks it's over here on the edge, and then yeah, at that point it just says I'm done. I'm gonna close that. But yeah, so you can play around with this. I love Anish's face of disgust at the end. But yeah, so you can play around with this. Like I said, you can also shoot. Yeah, so you can also come in here and if you want to add another video, I just recommend that you modify this run test script. This is just the initial. All thing this does is just publishes the initial bounding box. So you just where it is in pixel coordinates, the center, and then like the size. So it's a square, and that's where the center point was on the very first frame. So you can just add in a second one. For example, I just have it hard coded to test one right now. So if you want to test different videos, and then again, also just to show the beauty of Docker here. Oh wait, I was already there, so I can just do this. Yeah, so you see I made those changes inside the container. This is on my host, and those changes are all there. So I can come back here and go back to CSRT. And then in theory, yep, and then those changes there show up. So it's exactly like if you were editing locally. Yep, and then again, this is just showing CSRT. You can see how well it does. Yeah. Did anyone have any questions? Were you guys able to get this running? If you had any issues, just let me know. I tried to make it as simple as possible. You just had to pull a Docker image and like install like 2 things. Also, I realized that the video might be like lagging for you on your guys' end just because of Zoom. But just be aware that it is not lagging on when I'm running it. It's like running at frame rate basically on my computer. Okay. I'm going to stop sharing then. Yep. If you guys are all good, I would say just maybe put like a green check, and then we'll move on. Sourish, how are we doing on time? I know we have to do your tutorial now.
Yeah, we have around 30 minutes. I think it should be reasonable, probably.
We have about 30 minutes left. Oh yeah, it's 11 o'clock. Yeah, so I think at this point we can move on, and people can, if people haven't got it running at this point, they can do a free time.
Okay, so should I share my screen then?
Yeah, go for it.
Okay. Okay, so this tutorial will help you implement a backbone network for an object detector. So basically, like backbone networks are good for image classification. So this collab introduces image classification, and the first two models are predefined, and it introduces TensorFlow's sequential and functional API. So if you're new to TensorFlow, if you follow along the tutorial sequentially, you will get a hang of how TensorFlow models are created. It's super easy and very intuitive to understand. The first model will overfit on the dataset, and the second model introduces dropout and data augmentation to improve validation accuracy. And the third model is the one you're supposed to implement. It's a ResNet architecture. So you're supposed to implement a ResNet 18. I have added in the sections where you should add your code. And I've also added helpful comments and links to documentation and the original paper that should help you implement the ResNet. So you are supposed to just follow these 4 steps here, and and report the final validation accuracy on the training set and the accuracy on the test. So it's the dogs versus cats classification task. And once you have an initial model, and once you have the validation accuracy and the test accuracy, you can update this sheet